Welcome to Lesson 28, Chem 222 cadets. We are going to cover fundamentals of spectroscopy. It is the 17th of April. With Lesson 28 comes a deadline. Please remember, results report 6 on the potentiometric titration of iron is due today. Please upload to the team's website. If you have any difficulties doing that, send it as an email attachment to Captain Friday and myself. With today's lesson, we're going to talk about basic spectroscopy and the different instrumental methods of analysis that have been developed to exploit the interaction of light with matter. We'll cover the fundamentals of wave theory and light. We will talk about quantum mechanics and the discrete energy levels that our atoms, molecules, ions, and subatomic particles exist in. We will talk specifically about the UV visible absorption spectroscopic methods, including the theory of operation, which electron energies we are perturbing, and how we exploit that to gather information about atoms, molecules, ions. We will look at the design of an instrument, the components within, and then we will look at applications, specifically quantitation using Beer's law. There's some nice resources on Khan Academy regarding general spectroscopy as well as UV visible absorption. So please go to the URL provided here for further information. So electromagnetic radiation, it's a form of energy, light energy. So we know that via Planck's law, that energy, E in this equation, equals Planck's constant, known value, times the frequency of light, that's nu. Okay, we know that lambda nu has got to equal the speed of light. So we can substitute in that equation and derive energy equals Planck's constant times the speed of light over lambda. So very important relationships. Energy is directly proportional to frequency. Energy is inversely proportional to wavelength. And when using Planck's equation, just recall all of the units that are appropriate. The final term in this equation, when we do infrared spectroscopy, we deal with wave numbers. So this nu with the wiggly line, that is a wave number in inverse meters. So the electromagnetic spectrum, when organized from most energetic to least energetic, at the very left is most energetic. So at the left, this is radiation that has the largest energy. Okay, because frequency is proportional to energy, on the left is radiation of the greatest frequency, and on the left is the radiation of smallest wavelength. As you go left to right, we're going to end up with light of the least energy, least frequency, and largest wavelength. So in going left to right, the most energetic radiation are gamma rays, followed by X-rays, ultraviolet, the visible spectrum, infrared, microwave, radio waves, and then longer radio waves. So we have developed spectroscopic methods that are going to perturb subatomic particle energies and molecular energies, which is going to exploit interaction of those particles with different regions of the electromagnetic spectrum. So starting with least energy, so radio waves, okay, all the way down here. When we focus radio waves onto atoms, molecules, and ions, we are going to perturb the quantized spin states of our nucleus. Remember, the nucleus contains protons and neutrons. If we increase the energy, we are now going to perturb the rotational states of molecules and polyatomic ions. As we increase further in energy, into the infrared, we're going to perturb the vibrational states of our molecules. And you can think of bonds as little springs and existing in different energetic states based upon the ability to stretch and bend those bonds and move them in different directions. Next is the visible spectrum, in which light is going to be able to penetrate and perturb valence electron energies. So the electrons outside of the core. Further and more energetic ultraviolet light, okay, also perturbing the valence electron energies, but those of greater energy separation. With X-rays, we are now penetrating the atom or the molecule all the way down to the core electron energies. So we're going to perturb core electron energies. So we have spectroscopic techniques that have been developed for the interaction of light with matter in all of these regions of the electromagnetic spectrum. This is a nice summary of all the instrumental methods of analysis that have been developed to study the interaction of light with matter in different regions of the electromagnetic spectrum and involving different phenomenon of that interaction of light with matter. Starting with our absorption techniques. Okay, when we irradiate radio waves onto atoms, molecules, we perturb the quantized energy states, spin states, of the protons and neutrons in our nucleus. This forms the basis of the technique known as nuclear magnetic resonance spectroscopy, NMR, which is the chemist's version of an MRI. There is also electron spin resonance and microwave spectroscopy. If we get up into the infrared and measure absorption, okay, we are looking at perturbation of the rotational states of molecules and polyatomic ions and the vibrational levels. This forms the basis of Fourier transform infrared spectroscopy, in which we get structural information about molecules and polyatomic ions. Absorption in the ultraviolet and visible is going to give us information about the valence electrons involved in bonding. Okay, these are the electronic energies. So we get generic information about structural features like a carbonyl group or that kind of thing engaged in a molecule or in ions. The absorption of X-rays lead to X-ray spectroscopy. That's perturbing, instead of valence electron energies, now we're down perturbing core electron energies in those filled subshells. And gamma rays, that technique is Mossbauer spectroscopy. There are other methods. We can look at the emission of light after we excite it, and that gives rise to techniques such as X-ray fluorescence, XRF. And then we have other types of phosphorescence, fluorescence, phosphorescence, and atomic fluorescence, as well as chemiluminescence. So these are some very critical methods of analysis that are used to get all kinds of important information about species within samples. The remaining instrumental techniques that exist involve not only the absorption or emission of light, but different phenomenon of interaction of light with matter, such as the diffraction of light. And this includes the technique of X-ray diffraction, XRD, in which we can piece together the crystal structure, the distance between individual atoms in a crystal structure, the bond angles, etc. And then in the UV visible spectrum, we have refraction technique, refractometry. And if light is scattered, These two techniques help us to decipher the size of macromolecules. And finally, we can study the dispersion of light in the ultraviolet visible to give us some idea about the optical rotary nature of species. So to understand why light is absorbed or emitted, etc., we need to understand that atoms, molecules, ions, electrons, protons, neutrons exist in what we call discrete energy states or quantized energy states. So if a photon, such as the one here, comes in and interacts with an electron that's in a ground state, and remember it's going to be in the lowest energy state because that's where it's most stable if it's closest to the nucleus down here. The most stable place for electrons to be is in whatever orbitals are unoccupied and closest to the nucleus. So if that electron absorbs the energy from that photon, it gets excited to a new energy state, higher in energy, and that difference in energy is equal to the energy of the photon, which we represent by h nu. So that involves the absorption of a photon, and we would see a spectrum like the one over here. So if you're looking at the absorbance of light as a function of wavelength, okay, we're not going to absorb much light unless we get to this precise amount of energy. So at this precise wavelength, that's our lambda max, that's the wavelength at which the energy is equal to this exact amount right over here. With emission, we excite a particle to a higher energy state, and after some time it settles back down to its original and most stable energy state. When that happens, a photon is given off in this magnitude of energy right there. So with an emission spectrum, okay, when we plot the intensity of the emitted light as a function of wavelength, okay, you're going to see a maximum occur, once again, at a particular wavelength for that emitted radiation that correlates to the energy of the photon given off. So focusing on the ultraviolet and visible spectrum, some of the applications in studying the absorption of light in that region includes the technique of atomic absorption spectroscopy, known as AAS. Chemists love acronyms because we don't like to say long phrases. Atomic absorption spectroscopy is going to perturb the atomic energy states of our valence electrons. So, for a sodium atom, okay, these are the different atomic orbitals for sodium. Remember the 1s and 2s orbitals are filled. This is element number 11, so we have 11 protons and electrons in that species. So we can excite our valence electrons between the different atomic orbitals, such as the 3s orbital to the 3p. Okay, remember there's degenerate orbitals. And so the amount of energy required for that excitation occurs at known wavelengths and predictable wavelengths. So what we're looking at on the right is the AAS spectrum, the absorption spectrum. Absorbance is a function of wavelength, and so when we excite a valence electron from the 3s to the 3p, it happens precisely at that wavelength, 589 nanometers, or 589.5 nanometers. So this is the absorption spectrum of an element. And by knowing where those magnitudes of absorptions occur in terms of the wavelength, we can identify the species present. The remainder of today's lesson will focus on the technique of UV visible absorption spectroscopy. We'll come back and look at atomic absorption at a later time. That's chapter 20 in your book. So, for UV visible absorption spectroscopy, the main application of this technique is to gain information about the structure of molecules and polyatomic ions. We can also decipher information about transition metals and the complexes that they form. As the name implies, we are going to be measuring the absorption of light in the visible and ultraviolet region. So if you'll remember your kindergarten lessons, in the visible spectrum, we have red, orange, yellow, green, blue, indigo, and violet. So in terms of energy, starting with the wavelengths in nanometers, okay, the longer wavelength, so if we come down this list, we are increasing the wavelength of the light. Therefore, we are decreasing the frequency and we are decreasing the associated energy of that light. So if you will remember Roy G. Biv, in terms of energies, red, least energy, longest wavelength, violet, most energy, shortest wavelength. So we are going to look at the theory of operation of the technique known as UV visible absorption spectroscopy. This is a technique that's particularly useful to getting information about molecules, structural features within those molecules, and polyatomic ions. We are perturbing electronic energy states. These are the energy states of valence electrons. If you will, when you look at the total energy of a molecule, it has contributions coming from the electronic energy state. There's a contribution coming from the vibrational energy state, and there's a contribution coming from the rotational energy state. Okay, we can study the vibrational energy states if we use infrared radiation, and the same with the rotational energy levels. But the magnitude of the electronic energy levels is up in the ultraviolet and the visible spectrum. At the left, you are looking at different electronic energy states for a molecule. Down here, this is the ground state. For that species, okay, ground electronic state. And up here is an excited, the first excited electronic energy state. So if you hit this molecule with enough energy, it's going to jump to the excited energy state and absorb a photon. Okay, you will notice embedded within any of the electronic states, there's a series of vibrational energy states. So when that excitation occurs, not only do we change the electronic energy state, but we also change the vibrational energy state. So we started here at a vibrational state of 0, and up here we end up with a vibrational state of the second, more highly energetic state. So you're getting simultaneous change in the electronic energy state as well as a vibrational energy state. So to understand this better, when two atoms come together to bond using their valence electrons, okay, Each atom has its own set of atomic orbitals. Okay, those orbitals blend to form a set of molecular orbitals that we use for bonding. The types of orbitals that form, okay, remember if you have a sigma bond, that means we had direct overlap of two orbitals. We call that head-to-head overlap. If you have orbitals that have lobes like the p orbitals and they come towards each other, you get side-to-side overlap, and that is a pi bond. Okay, so the kinds of molecular orbitals we form, lowest in energy down here, we have a sigma bonding orbital. We have some pi bonding orbitals. We have some pi anti-bonding orbitals. And the most energetic possible energy state is the sigma anti-bonding orbital. So when two atoms are bonded to each other in a molecule, their electrons, however many there are, let's just say that there were 2 over here and 2 over here. So I have 4 to distribute, and so they would go in 1, 2, 3, 400 rule. Okay, so we have electrons sitting in different energy states, and so we can excite, for instance, any one of these electrons to any of these other energy states. I could excite these electrons to that state or that state, and so we have sigma bonding to pi anti-bonding, sigma bonding to sigma anti-bonding, so on and so forth. Okay, so the characteristic transitions between those sets of molecular orbitals and the typical range in the electromagnetic spectrum where those transition occurs, you will see that for single bonds, those are sigma bonds, okay? If we're looking at sigma, sigma star transitions, those are going to happen in the ultraviolet, okay? Remember, those were the transitions that had the greatest amount of energy. Commonly, if we have a non-bonding orbital transitioning to a sigma anti-bonding orbital, that's going to involve less energy. Okay, we will see that whenever we have lone pairs of electrons on species. So when we start introducing oxygen, tends to form 2 bonds and have lone pairs. Nitrogen tends to form 3 bonds with 1 pair. And the halogens tend to have at least 1 lone pair of electrons, if not more, such as that. So those transitions tend to happen in the 160 to 260 nanometer range. Then we get into unsaturation, double and triple bonds. Okay, when we have, remember, this is formaldehyde. Remember, a double bond is 1 sigma and 1 pi bond. Okay, so with unsaturated features in our molecule, double and triple bonds, we start introducing pi bonds. And so we start seeing these pi orbital transitions. These occur down in the visible. So a pi-pi star transition traditionally happens between 200 to 500 nanometers. Such as in these features of a molecule. And if we go from a non-bonding orbital to a pi star orbital, that can extend up into 600 nanometers. So this slide simply shows spectra of some dye molecules that have a lot of conjugation alternating double and single bonds, which results in characteristic spectra absorption features in the visible spectrum. So you're looking at 3 different dyes, And for instance, this cyanide iodide species, the blue spectrum, here's the structure of that species, and you get several absorption maximums. There's one that occurs at this wavelength, and now we've got another that occurs at this wavelength, and we have a feature over here at this wavelength. So that is due to those characteristic valence electron energy transitions between the molecular orbitals. Another application of UV visible absorption spectroscopy is for the identification of transition metals. Remember, transition metal ions tend to have empty d orbitals, and so we're going to exploit the excitation of electrons within the d orbitals. So in general, if you have some metal ion and it gets complexed by a ligand, and you form a complex such as the one here, okay, you're going to be perturbing the d orbital energies of the metal ion. So if we start with the free metal ion before we complex it, those d orbitals all have the same energy. But if we bond the metal ion to a ligand, okay, we are going to split out the d orbital energies into different energetic levels. So if we form a tetrahedral complex, that is the metal ion, and put 4 ligands around it in a tetrahedral fashion, those d orbital energies split according to this, where now we have a separation of energies of that magnitude. If we put 6 species around our metal ion, we have 2 in the axial position, 2 in the equatorial, 4 in the equatorial. The splitting amongst the d orbitals takes on this configuration in which the difference in energy is that magnitude. Or if we put 4 things around our metal ion and it's in not a tetrahedral configuration but square planar, then the splitting we get looks like this. So you can see that these energy differences are different. And so we can decipher information about the nature of the complex that forms based upon the magnitude of those energy differences. One other interesting application in studying transition metal ions, and remember those are the beautifully colored ions. Think about copper and the blue solution, and nickel and the green. So obviously these are species that do absorb in the visible spectrum. And one other interpretation and analysis we can decipher important information about our transition metals is if they're complexed by different ligands. So in this case, I have water as my ligand. But if I switch out cyanide ion for the water and end up with this complex, the splitting pattern of the d orbitals changes based upon the ligand that we complex. And so what you're looking at here is a relative ligand splitting field strength. So on this end, the cyanide ion is the strongest, the iodide ion is the weakest, and that pertains to the magnitude of the energy separation of the d orbitals. So you would have the biggest separation for the cyanide ion, and you would have a much smaller separation for the example in this case of water, because it has a weaker ligand field strength. So you can see the potential for us to derive important information about the complexes that transition metals form by looking at their UV visible absorption spectrum and at what wavelength do we see an absorption band in the visible spectrum. And there's your lambda max. The second area we want to focus on with our UV visible absorption methods is the instrument and the components within the instrument. You are looking at what we call a block diagram of the instrument. The most simple design is for us to start with a light source. Okay, we must have some source of the UV and visible light that we are going to irradiate our sample with. Okay, the source lamps typically are what we call broadband. Which means they are going to emit radiation over a broad range of wavelengths. So we are going to need as a second component what we call a wavelength selection device. We only want to radiate our sample with a very narrow range of wavelengths. We want to select a particular wavelength and measure the absorbance at that one wavelength. And then we are going to change the position of our wavelength selection device so that we let not just this wavelength through, but then we're going to let this wavelength through, and then this wavelength, and then this wavelength, so on and so forth. So we're going to scan over a range of wavelengths and collect the spectrum accordingly. So our second component is a wavelength selection device. Okay, then we're going to let that light be focused on our sample of interest. Our sample of interest contains molecules or polyatomic ions that have the capacity to absorb radiation of certain wavelengths. So we're going to measure the power of the light before we have a sample in place and then after. And however much light does not get absorbed is going to hit what we're going to call a detector. So these typically function in a manner such as however many photons hit the detector, that's going to create an electrical current that we can measure, and based upon the number of photons that hit, that's going to impact how large the current flow that happens. With the single beam design, we must always put a blank sample in first, record the response, calibrate our instrument, and then put the sample in. That can be a cumbersome procedural method. Alternatively, our instrument can be a double beam design in which we have a sample path and a reference path. So in this design, as in the previous case, we have a source lamp that's going to emit a broad range of wavelengths typically. We need wavelength selection, and that's going to be our monochromator such that it's only going to let a particular wavelength come through as a function of time. To create the two different optical paths, we have what we call a chopper. It's a rotating blade with a mirror on it, such that half the time as it's rotating, half the light's going to go in this direction and pass through your sample. The other half is going to be focused down onto this mirror and get reflected over into a blank. So once that radiation passes through the sample up here, it bounces off a mirror and recombines with the beam coming through the blank. And so we have little segments in time of sample blank, sample blank, sample blank. The detector is going to respond to the photons coming in, and the computer is going to compare the power or intensity of the light coming through for my sample. And let me go back and use a different symbol. The power that comes through of my sample relative to the power that comes through for the blink. So it's going to correct for any stray radiation that hits the detector, or if my solvent absorbs little tiny amounts of the radiation, it will correct for that. This table gives a nice summary of different source lamps that are used in spectroscopic instruments, typically for UV visible or infrared absorption techniques. So the specific ones most commonly used, a hydrogen and a deuterium lamp is going to give us emission of radiation in this range. So it's pretty much the visible spectrum. Tungsten lamp gets us into the ultraviolet as well. Xenon arc down to 200, so that's the ultraviolet and visible. If we need a source lamp for infrared spectroscopy, we're going to use these source lamps. So this is for infrared. Once again, these are ultraviolet and visible spectrum source lamps. And then if we're doing atomic absorption spectroscopy, we need a line source. We are actually going to, instead of emitting a range of wavelengths that focuses on our sample, we are going to irradiate with a singular wavelength. That's a hollow cathode lamp. And then there are some other lamps that we typically use for our fluorescence and phosphorescence techniques, and we'll talk about those later. The next component in our instrument serves the purpose of selecting a single wavelength out of the band of wavelengths emitted by the source lamp. The most common wavelength selection component is known as a monochromator. It is based upon the use of a diffraction grating in which we have etched on a mirrored surface, we have etched little lines at a known and highly precise distance. So the way it works is we have our source lamp out here. The broad range of wavelengths hits a slit so that only those wavelengths right there focused optically on that slit are going to pass into the monochromator. So the range of wavelengths will contact this mirror. Okay, this wavelength's over here, this wavelength's over there. It bounces off the mirror and gets focused onto the diffraction grating at this point and this point. Okay, based upon the length of the wavelength of the light, remember wavelengths, it's the distance traveled to complete one cycle. Okay, that wavelength relative to the spacing d on the diffraction grating is going to set up constructive and destructive interference depending on the wavelength. So as you can see, once the light is focused onto the diffraction grating, okay, some wavelengths are going to recombine and hit precisely. So the green one hits here and hits precisely on the exit slit. That is total constructive interference. Okay, and so the green light will come through. Okay, light of different wavelengths are not going to experience total constructive interference, and they will not be focused on the exit slit. You can see the blue will end up here, and the red is going to end up here and not get through my exit slit. So in this manner of the angle at which we position the diffraction grating, we can selectively allow certain wavelengths to get through and other wavelengths not to get through. In this particular instance, that angle position of the diffraction grating is such that the green light is getting through. Okay, if I change this angle, then I can allow the blue light to get through, or I can allow the red light to get through. So by scanning over a range of wavelengths, I am going to change which wavelength with respect to time is getting through the monochromator and being allowed to hit the detector. This is how we collect a spectrum. So our current that flows is a consequence of the number of photons hitting the detector as a function of wavelength. So starting at one end of the spectrum, okay, at this point in time, we record that data for the 300 wavelength, and then next. And in this manner, we scan over a range of wavelengths, collect data, and record a spectrum. The next component in our instrument involves the sample. We place the sample in a cuvette. The cuvette is typically glass or it can be quartz. We obviously need a material that is transparent. It's not going to absorb light in the ultraviolet and the visible spectrum. Quartz is ideal. It will not absorb radiation in the ultraviolet. They are more expensive than glass. We can also choose sample cuvettes of different configurations. This is a square sample cuvette. A square sample cuvette has the advantage over a round cuvette with respect to the fact that as the light hits at any place along the cuvette, the path length here, B, the width of the cuvette, does not change. If you have a cylindrical cuvette, notice that the light that strikes up here travels a little further than the light that strikes down there. So the cylindrical cuvettes actually are not the ideal configuration to maintain a constant path length, B, across the cuvette. So therefore you typically see these as square. We can design the cuvette for us to analyze samples that have flow. So if I'm an industry and I'm making a product and I want to know at a particular point in time during that production line what's in the sample, I can have it flow into this side. It flows in, the measurement is made, and then it flows out. You can actually heat cells so that you know the temperature and can do kinetic studies. You can analyze very tiny samples with microcells. Okay, but the standard sample cuvette for most common work is a square cuvette made of glass. You know, glass is going to be, you know, maybe $50 versus quartz, which can be really expensive if you have matching sample and reference cells. And the standard path length here, the width of the cuvette, is 1 centimeter. So a lot of variety in the cells that can be used, which makes the technique incredibly versatile. So the detectors that are used in our instruments come in a large variety of different types. The most common in a UV visible instrument is going to be a photomultiplier tube. Okay, how these work: your photon comes in, it slams into a dynode, an anode, a photoemissive material that's going to eject electrons once that photon transfers its energy. And so then those electrons get accelerated towards another electrode that's positive, that is applied a positive potential. So those electrons slam into this dynode, and even more electrons come off that surface, slam into that one, operated at a higher positive potential. This goes on multiple times, so it's amplifying the number of electrons that are being emitted, and so we get a current. So based upon how many photons hit, that's going to generate a current of a certain magnitude. The more photons that hit, the bigger the current that flows. A more sophisticated instrument is one in which we're not going to need a monochromator to select the wavelength, but we're actually going to let all wavelengths hit the detector at the same time. So instead of having to scan over a range of angles of our diffraction grating, we don't need to do that. We're simply going to disperse the light with our diffraction grating, and we are going to have multiple photomultiplier tubes at different angles coming off the diffraction grating. This is a diode array detector, so we have many different detectors positioned at different angles. This is going to allow us to detect all wavelengths at the same time. The huge advantage is we're going to be able to collect our spectrum very quickly. So we collect data for all wavelengths at the same time. And that can be a huge advantage, as we'll see in the next slide. With a diode array detector and the fact that we can collect a full spectrum instantaneously, we can exploit that by, instead of just collecting one spectrum, as is the case here, and you see we get a lot of noise, background noise in the detection. That's going to limit my ability to determine the height, magnitude of that band. Okay, so I can co-add multiple spectra. So since it only takes a fraction of a second to collect the spectrum, instead of collecting one, I can collect 4. If this is true random noise, the baseline is going to smooth out more, and I'll be able to get better data. 16 scans gives me a much smoother spectrum. If you would like to look at a list of the different detectors, or transducers as they're called, that exist for use in different spectroscopic instruments, this is a list. Our previous slide took a look at the photomultiplier tube. It is the most common. Okay, and here's the wavelengths over which the detectors respond, and the nature of the output signal. Is it a current? Is it a change in current? Is it a potential? And so you can see those that are going to be effective in the ultraviolet visible range, versus down here we're in the infrared. So those are the kinds of detectors we would see in those kinds of instruments. The last thing we want to do is give consideration to the application of UV visible absorption spectroscopy. We can derive both qualitative and quantitative information about the species present in samples. For example, you are looking at the spectra that result, the absorption spectra that result from, first of all, right here is a pure solution of chromium-3. So you see there are 2 characteristic lambda max values for that species of interest. So we could identify potentially that chromium is present by virtue of the fact that we get absorption maxima at those 2 wavelengths. Okay, we also see in this sample in a different sample, sorry, we have pure cobalt, and that species gives us an absorption maximum here, okay, more like around 500 nanometers. This should be in nanometers. Okay, so qualitatively, I might be able to decipher that cobalt was in that solution based upon the position of this lambda max here. We can also do quantitation based upon, if we extend a baseline across an absorption band and you measure the difference in the absorbance, that is going to be in proportion to how much of that ion is present. And if you have a solution that had both of these species, you would get an absorption spectrum that looked like this. Okay, where obviously the absorbance at each and every wavelength is going to coadd. So you're seeing the feature from the chromium here. You see a rise in the cobalt here, and then once again the feature from the chromium here. So we can actually do quantitation of more than one species using these methods. So the quantitative application of any absorption technique is the exploitation of what's known as Beer's law. Once again, here is the schematic diagram of our instrument. You have light source, okay? Then we have a wavelength selection device that's going to allow one particular wavelength to pass through our sample. We measure the power of the light when no sample is present. That's the incident power, P sub 0. Then we put the sample in place and measure the power that comes through, and that light hits the detector. So P is the power transmitted, P naught is the power incident. Okay, the transmittance is the amount of light that hits the detector. So remember that the transmittance plus the absorption has to add to 1. Okay, either the light was absorbed by the species in my sample, the molecules are polyatomic ions, or it was transmitted. So the transmittance and the absorption have to add to 1, or if you wish to work in percentages, percent transmittance plus percent absorption have to add to 100. We define transmittance as the power of the light that gets through divided by the power of the incident radiation if no sample was present. It's that ratio. We define the absorbance, A, as the log of the ratio of incident power to transmitted power. This is the negative log of the transmittance. And if you wish to work in percent transmittance, remember percent T equals 100 times transmittance, or in other words, transmittance is percent T divided by 100, and if you substitute that into this equation, you get that absorbance equals 2 minus log percent T. So this is the equation for Beer's law. The absorbance of the sample is directly proportional to the concentration of my species of interest in molarity. So however many molecules I have per liter of solution, okay, the amount of light that gets absorbed is going to depend on the concentration in molarity. Okay, It's going to depend on the path length. Okay, obviously B here is my path length of my cuvette in centimeters. Okay, and so the absorbance is going to be proportional to concentration. It's going to be proportional to the path length. And the constant of proportionality is something known as an extinction coefficient. Okay, it's also referred to as the molar absorptivity. This is a constant and known value for a given species at a particular wavelength. Therefore, Veer's law, absorbance equals extinction coefficient times path length times concentration. That also has to equal 2 minus log percent T. Okay, so experimentally, we measure the transmittance. We know the path length of our cells. If we know the species of interest, either we already know the extinction coefficient or we can actually calculate it from known solutions. And so by measuring the transmittance and knowing these values, I can calculate the concentration of any species of interest. To do quantitation using UV vis absorption spectroscopy, we approach it like any other quantitative technique. You prepare a set of calibration standards of known concentration. In this case, iron is my unknown, my analyte of interest. Okay, you measure the absorbance for these known calibration standards. You plot the data. Okay, you get a linear regression equation in which A, absorbance, is your y-axis value. X is your concentration of iron in this case. And B is simply your y-intercept. And so if we know the slope and the y-intercept, I can measure the absorbance for any unknown solution and solve for X, which is the concentration of iron in any unknown solution. A final application of UV vis spectroscopy is for the analysis of a mixture of more than one species. What we are looking at here are, first of all, a solution of pure chromium, a known solution with a known concentration. Okay, you analyze that first. Okay, we measure the absorbance of this known chromium solution. I know the path length of my cell. I know the concentration of the chromium, and I can calculate the extinction coefficient for chromium at this particular wavelength. So you can determine the extinction coefficient here for chromium, and you could also determine that value at a different wavelength, such as here or here. Then you can get a pure solution of cobalt. Okay, we know the concentration of this cobalt solution. I measure the absorbance at different wavelengths, such as here and here. Sorry, it'd be up here. Okay, so once again, if I measure the absorbance, I want to know the extinction coefficient for the cobalt at this particular wavelength. I know the path length. I know the concentration of the cobalt, so I can calculate the extinction coefficient. The next step, we are going to collect a spectrum for a mixture of these two ions, but I do not know the concentration. The result is this spectrum up here. So what I do is I pick two wavelengths that aren't exactly at the maximum of either, but are kind of halfway in between. I'm going to pick these two wavelengths, and I'm going to measure the absorbance. So this is the absorbance at lambda 1, and this is the absorbance at lambda 2. Okay, so there's contributions to that absorbance coming from both species. So I have two equations at lambda 1 and lambda 2. Okay, the absorbance at lambda 1 comes from the absorbance of cobalt at lambda 1 plus the absorbance from the chromium at lambda 1. I have a typo here. This should be a chromium on this extinction coefficient. Same down here. Okay, we can do a similar thing at this wavelength and this absorbance, so equation 2. And so because I have already predetermined the extinction coefficient values at lambda 1 for the two species and at lambda 2 for the two species, that is known. The path length is known. The absorbances are measured. And so there's only two unknowns in these two equations. The concentration of the chromium here, and the concentration of the cobalt here and here. You can solve those two equations for those two values and determine the concentrations of those two ions in the unknown mixture. A final note on the application of absorption spectroscopy and the fact that we do get deviations from Beer's law. So traditionally, absorbance is going to equal an extinction coefficient times path length times concentration of species of interest. Ideally, we want to see linearity between absorbance and concentration. That's the ideal. But the reality is sometimes we get deviations where it's no longer linear and it either bends over in a negative direction or bends upward in a positive direction. So what can cause those deviations from Beer's law? First and foremost, not working at lambda max. So if you are measuring absorbance over a range of wavelengths, okay, we are assuming that this is a constant value. Okay, so if you're at the top of a broad absorption band, that's a good assumption because the extinction coefficient at this wavelength doesn't vary a whole lot from the extinction coefficient at that wavelength. However, if you are on a shoulder, okay, down here, then the extinction coefficient here versus here does vary substantially. So the assumption that those are constant is no longer valid. This will cause this deviation from Beer's law if you're working on a shoulder as opposed to the top of the flat absorption band. Other sources of deviations from Beer's law: sometimes light can originate in the instrument and bounce around and somehow get to our photomultiplier tube. Okay, and that light didn't go through our sample. So it's going to increase the power of the light transmitted, okay, which is going to cause lower absorption values. So stray light hitting the detector can also cause negative deviations from Beer's law. And the final one is if you are working with a solution that's too concentrated. Remember your sample cell, and you've got molecules at a certain concentration. And so we want the absorption to be proportional to however many molecules are present. But if too many of these molecules are crammed in here, not all of them have the same opportunity to absorb a photon. and so you would get bending over of the Beer's law curve if your solution was too concentrated. So this ends all of our practical considerations of absorption techniques in general and UV visible spectroscopy in particular. Thank you for listening.